Okay, welcome everybody. This is our presentation, Once More Unto the Data Breach. This is about navigating investigations of unconventional data sources. I am David Sigmundson, an Associate Managing Director at Kroll, where I do weird things with weird data all the time. This is actually my first time here at SANS, my first time here in Texas. The first clue is when I got off the airplane wearing a sweater. And with me, I have Anthony Woodburn.
Hello, I'm Anthony. I'm a senior associate at Kroll. I pretty much work with Dave almost exclusively, working on weird data, deep diving documentation, and pretty much hands-on in whatever I get into.
And I'm Devin Ackerman. It is an absolute pleasure to be back. I was last up on stage with all of you back in 2018. I did a presentation on BECs with Microsoft 365. I am the global head of incident response for Kroll. I know a lot of you in this room. I know a lot of us have collaborated through the website, through About DFIR. But again, it's a pleasure to be back.
Awesome. Let's get with it. And that will be a tough talk to follow, the keynote to kick us off. Unfortunately, there is no face punching in what we're about to talk through, but it's, I think, going to be exciting either way. And as you all know, digital forensics is a science built on decades of research, experimentation, validation. We have 16 years of these conferences to fall back on in terms of experience. When we're getting into some of these novel data sources, new data sources, we're going to have to think about how we're approaching those situations, as we do not have that same experience. We do not have that same documentation. And that's really where we get into framing our investigations. And again, we're talking about data sources that may be novel, new to you, or something that you do not have any documentation to rely upon. And with that, we can get into framing our investigations. This is very elementary. We can talk through this very quickly, but all forensic investigations will have a goal, the actual impetus, the reason you're actually going through and performing this investigation. For the context of the three of us on stage, this will at least relate to a data breach. There was some actual breach. There is unauthorized access to a network, to a system, and we're there to really identify if a threat actor had accessed that content or exfiltrated data. With that goal in mind, we talk about the outcome, the actual product of our investigation. And for us, that is actually coming up with evidentiary material that indicates there was some scope of breach, some scope of unauthorized access. So that's our outcome for any investigation. And when it comes to the data, actually identifying, preserving, understanding, manipulating as necessary, reporting on that data, that's the forensics, that's the meat of it. That's why we're all here. And as we're getting into these novel data sources, it may be quite possible that you can do absolutely everything right and still not have enough information to really come to a conclusion. That's just the nature of working with data sources that aren't necessarily forensic sources. And with that, we do want to say we wish there was a more standard forensic approach to dealing with data sources that were not forensic sources. And this is where we come to just the first mental model that we'll refer to throughout this presentation across our case studies, something that we will call evidence pathways. And this is very easy to communicate, very easy to understand, easy to recognize. And the point is that you can generalize the data sources that are coming to you as an analyst, so you actually can understand what you're working with, understand what assumptions may be brought into this process by handling that data. And by direct example, we can go and identify these quite quickly. A primary acquisition source. This is something that is very objective, very proximal to you as an analyst. Think of something like an actual forensic image. Once you actually take an image of that content, it will be the same every time you look at it. You know exactly how you got it. You performed that imaging. You understand those artifacts. Anything host-based, anything within your network perimeter where you can directly touch and address is going to be a primary acquisition. And this will start to make more sense as we get into a secondary acquisition, where we talk about really service providers brokering this information to you. So something like Microsoft 365, any of those logs where you press a button, you configure that output and it sends you some data back. That's a secondary source. Again, you no longer have access to that underlying data, but because you are paying for this service, you may be able to get something back in return. And this means that there can be limitations on that data that you do not control. The actual application versioning, the licensing, the software level or service level agreements, all of that can impact what you get back in return. And this means that if you go to repeat that acquisition, even at different times for the same configuration, you can get different results. And this brings assumptions into our processes that we need to be aware of and actually address. And moving furthest away from these very objective sources is our tertiary acquisitions. This just means that the integrity of the information you're actually getting back is unknown. You don't really know how to qualify it. So there's spoilage, there's tampering, there's misinformation that are all quite possible in here. From an actual example, anything from a threat actor, it should probably be considered tertiary acquisition. This is where data from adverse parties, perhaps as a litigation, if you're being sent a bucket of data responsive to some document corruption, this should be considered tertiary. They're adverse to you. You don't want to start believing everything they sent you is fully factual and complete. And tertiary is really where we get into this being a pathway. Primary acquisition is being directly, you are performing it. Secondary acquisition, something is being sent to you directly from a party that you should somewhat trust. And as a tertiary acquisition, it could be either of these two sources underlying. And as it goes through another party that you don't trust, it is now a pathway. And that's going to be the most important element to you, because your foundation of your investigation will rely on this data, and you must understand that it may not be fully trustworthy. But what does this all mean anyways? It just means that you should be aware of the data that's coming to you. You're going to start checking your assumptions. You're going to seek documentation. Forensics being a science, there are ways to go and actually validate the data coming to you, trying to make these associations, to make your investigation as sound as you can make it. So obviously, independent validation will always be king. If you can perform experiments to determine any pieces of information, you're going to do so. You're going to write that information down, make it available to your colleagues. If you write enough things, you might be able to write a book.
One of the fun parts that we're going to get into in this presentation over a couple of case examples to kind of reiterate and build upon what Dave has started talking to us about here is really fundamentally the examples that I think all of us probably have had a background in dealing with dead box forensics, right? We're not going to spend too much time on that, but it's really the examples of 2 and 3 that we're going to spend time on, and exactly things that I've learned over now 2 careers, both with the FBI. Sorry, you have now 2 FBI speakers on stage, but the FBI, but also consulting, right? It's very interesting to approach forensics incident response from really both the public sector and the private sector, because you frankly use very different approaches. And so it's given me a very interesting way to kind of now document that in the book for those of you that are interested. But the bottom line is the stories we're going to tell you with the case examples focus on really the second and third pieces.
Thank you, Devin. And as we move through these case studies, we do want you just to take note about what we believe these evidence pathways are and how they're actually impacting our investigation and analysis of this data. And with that, Anthony.
So our first case study is really looking at the primary technical documentation and independent validation. So we had a client that had their complete number of repositories breached. And for those that don't know, a Git repository is a distributed version control system, or as Git likes to call it in its man page, a student content tracker. It's often used for collaborating code. It looks very much like the example that's on screen there, pretty much just a directory with a hidden Git folder. So the client had about 300 repositories that were breached by a threat actor. And the big question for them was any their concern was any proprietary information within that code? Was any sensitive data there? And there was also a concern that test data may not have always been test data. So what we're looking for here is to be able to answer the question of, what data is at risk and what is the level of difficulty to access that data? And is the format that we receive these repositories all that we have to worry about? Or since it's a version control system, is there more files and access that we don't have readily available to us? So obviously we're going to consult the documentation and we can find and identify some commands. So the first one is that Git provides a function that is a commit, which records changes to an index. And when those changes are recorded, it generates a 40-character SHA-1 checksum named object. Reading the documentation a little bit further, we can see that the objects that we're interested in are the commit objects, which is everything that was changed, a name of everything that was changed, the author, as well as the time that change was committed. And then we have blob objects in which the content of that actual change or the delta is available. So by reading the documentation, we can see rev list, which will allow us to get information from the repository itself, whether it is even a repository or get a list of the objects. And by feeding that to the cat file command, which allows us to get information about the individual objects themselves, we can begin to get a listing that we're going to want to write down and preserve for documentation later.
Quick question for the audience. How many of you have done forensic incident response investigations involving code repos, but specifically GitHubs? Quick show of hands. Okay, so one of the things you've probably dealt with from those of you who raised hands is ultimately then trying to figure out from a track change perspective, when was the code altered, potentially by a threat actor, right? To inject malware, to inject a redirect, to inject some type of C2, or when did the test data start to suddenly have real data? And I'm sure that for many of you that have done these investigations, it is always fascinating to run some type of automation against these repos and find all the hard-coded tokens, passwords, and secret keys that are now plainly available to the internet. It's one of the biggest things that traditionally we are looking for in these when companies are like, no, certainly it's all test data. This is perfectly fine on the internet. And then they're wondering how their AWS stack got compromised. Also, one more thing, any of the scripts we show on the slides, if you are interested in those, please don't feel you have to frantically take pictures or start writing those down. We have some examples of scripts we came up throughout these scenarios. Just email us, hit us up on social media. We'll get you copies happily.
Great. Yeah, so once I've been able to identify that there is a list of the changes reported within the repository, we obviously want to see if that those objects exist within the repository itself. So our rev parse command allows us to identify the actual path of that objects folder. And when you navigate to the objects folder within the hidden Git folder, you'll see your objects existing in potentially two forms, either within the pack folder or loose. It's packed is when those objects are pushed remotely. Loose is when those objects still need to be pushed. They'll be represented by the first two characters of the 40 SHA-1 checksum, and within inside those folders themselves will be the individual objects named after the remaining characters. So now we have a way to identify the objects folder. We have a way to list the objects. We have a way to check out to see if they have file residency. And now my concern is what is the content of those objects accessible? So we only need to use enough of the object hash when we're feeding it to cat file, and we can actually identify the object type, the contents of the objects, and the as well as other details about the type, the size, and if an object exists itself. So now that we've gone through, we've been able to see that there is more data at risk than we initially could have assumed if we would have just fed the Git repository into a review platform. We've been able to see that the level of the barrier to access to these repositories is very low. If you have the repository, then you have access to the content. And what we're going to be looking to do is wrap code around those commands to be able to start creating tooling to answer those specific questions that we have about the data. So this is just a bash script wrapped around some of those questions that we initially had, where we're making sure that we're preserving the listing so that we have a reference and context around the data. We're running through each of the objects within the object database in the GitHub repository to make sure that we're capturing that content, and we're interested in the commit and blob content. And alongside that, we're making sure that we are creating a metadata file about the content itself, because that's a very important fact to make sure we have alongside unconventional data. And then any other time that we come across a command of interest or any kind of information that we can pull, we want to make sure that we're writing down that pathway and those questions that we've been able to answer with that, even if it's not exactly relevant to the question we're trying to answer at the time. So that was obviously not a complete code solution. It's an iterative process. So we want to make sure that we're checking our assumptions. And was there any point in time where maybe the data that would be in a repository wouldn't be captured by this objects list, and that it would be excluded, and we need to make sure that we're including those. What changes to the code base were made during the dwell time? Who made those changes? That might be an interesting thing to include alongside those that metadata file. And in this case, we also, within the code, we had base 64 images that was the test data that we needed to extract from that code itself. So even though you may be looking for images, they may not be representative in the original format that you would be expecting. So one thing that we do want to point is that the metadata alongside unconventional data is exceptionally important. Being able to categorize and make those determinations about unconventional data helps, lawyers, counsel, client make decisions about what's relevant or not. If I had just taken all of the data that we had gotten from all 300 of those repositories, we would have had 2.4 million files going to our early case assessment. But by getting those parties involved and getting the right keyword searches with the subject matter experts, we were able to reduce our review population to about 4,000 documents going forward. And really, it's just a process of trying to identify first-party documentation that allows you to have commands that you can wrap with code that can save you a lot of dev time, and we're kind of coming up with a unique solution.
Thank you, Anthony. And what I appreciate about that example is that you do start to bring in context about what processes follow you, and you do provide enough information to make sure that their processes can kick off with all that in mind. And on to our second case study is a Slack compliance export. It's just a show of hands, who here has actually dealt with this format before? Oh, there's at least 3 hands. That's good. So talking about the Slack compliance exports in the context of our investigation, once again, this is a breach. There was a period of unauthorized access from a series of users that were in a Slack workspace. And again, this is the chat messaging platform, just like the one we're using here for the conference. And as an outcome, we had to go and identify exactly what might have been exposed to these users. With that, we can then recover that subset of information and push it into review for privacy regulatory issues. And then we get to the data, which again is the meat of all these discussions, the Slack compliance exports. To start, you have to really consider how you're getting this information as a very much secondary source. So if you are the owner or administrator of a Slack workspace, you can go and try to request access to your own data. Unfortunately, you will find that the data you get back is fully limited by how much you're paying Slack. So if you have a Business Plus or Enterprise grid tier of license, you can actually access direct messages and private channels. Unfortunately, that is very much limited to another clause they have where it's gated as needed and permitted by law. Thankfully, if you have general counsel that will indicate this was related to some sensitive data review process and you pay them enough money to go and actually get your own data back, you can get your export in hand. And what does that look like? Well, it's a zip file. Within that zip file, you have hundreds to thousands of folders. Those folders represent channels, and you're maybe thinking that 1,000 channels in a Slack workspace must be huge. Unfortunately, no. It's a little bit of a combinatoric problem that if you have users in a Slack workspace and they have direct messages with each other, it quickly expands out so that each one of them can talk to each one of them, and each subset of people likes to talk to this subset of people. So you have thousands of channels relatively quickly. Within those folders that represent channels, you have JSON files. Hooray. These JSON files are named after the date of which those events occurred, and it wraps together a day's history per channel. And that's what you essentially have. There's an example on the right-hand side, which indicates the type of data you're expecting to see in here. Again, this is JSON structure, something that I expect most of us to be very familiar with and very familiar with actually investigating. But as we're generalizing this process, we really want to make sure that there is a structured way we can approach these investigations that can be repeatable, verifiable, and in the end, get the product which we really desire here. So alongside these JSON files, we will have 6 informational files. There's the users.json file, which as probably you would expect, this contains the details about the users. So their usernames, their user IDs, profile pictures, all that fun stuff wrapped together. We then have the integration logs, which indicate the types of applications and add-ons that may be included in this workspace. And that's all well and good, but as you go through this export, you see that it's entirely JSON. From the context of an investigation that we were provided, we were expecting to see attachments. We were expecting to see the content that would likely contain that type of sensitive information that would make this a privacy review. Well, unfortunately, it's not given to you. And as you can go back to first-party documentation, you will quickly see that no, they don't provide you those attachments. What you do have is a keyed URL in the messages in situ where those attachments should be that points to Slack's cloud-hosted resources. That's where your attachments are. So unless you take the time to quickly look at your data and identify this, you're not actually preserving that content. So what you must immediately do, and within as short of a time frame as possible, is go and pull back all those URLs, make sure you are retrieving those remote resources that are only hosted by Slack for as long as their retention is really willing to, or if those users choose to delete, and maintain that connection to where you found them in situ in those messages. Once you have that, you've actually preserved your data. And I know that there's a lot of applications over the last few years that have made this process a little bit more automated. They'll digest your Slack data, but again, we want to approach these from very generalized methodical processes. And what we do is as we get arbitrary JSON log data, whatever it is, and we haven't seen this format before, we go through a process of discovery, we go through a process of inventorying what is actually supplied to us. One of the tools that we are using right now a fair bit for just our quick inventories and assessments is Power Query. This is a Microsoft tool that's built into products like Power BI. It's built into Excel if you really want it, and it's a data processing and transformation pipeline. So within a few minutes, you can point it at a folder of a few thousand folders of JSON files and start pulling back information from those JSON entries, JSON blobs. And you can ingest from hundreds of data sources. That big list on the side you see there is all the sources it will automatically connect to and start pulling data. If you want to get fancy, it's got built-in SQL-like joins. It's self-documenting. And all this really means is that once we have data in hand, we can get through our process of discovering what information is provided to us very quickly. And one of the first things that we are going to do after we have an understanding of those fields is we're going to start validating that the information came to us from this secondary source is what we expect. And one of the most critical ones that we see within these breaches is just simple filters like date filtering. If there was a period of unauthorized access after those attackers have been kicked off this Slack workspace, we want to really make a cut, draw a line in the sand there and say content past this date is not going to be relevant to us. So within 3-5 minutes of actually touching the data, we could build out a little heat map to indicate that yes, all the data we have falls into the actually relevant time span. Anything past that, not going to be included. If you want to get deeper into your investigations, you can build out other heat maps that indicate perhaps gaps within your communications. And on the bottom right, it's a simple heat map that includes the days as well as the hours of the day. So you can see if there are gaps in your collection, gaps that should ask or make you ask questions about the data provided to you.
And we'll give three very succinct examples of this. So just as Dave was just pointing out on the trust but verify aspect of this, right? Getting a download dump from a third-party provider, potentially making an assumption wrongly that it has all the data, and then identifying it actually is missing. So we had a case, we had an engagement where we were tasked by outside counsel to ultimately identify all the files being shared as attachments in the channels that were at risk due to unauthorized access. When we got the file back, realizing it was fairly light, we realized that those documents were missing, and then we had to do that kind of tertiary collection. It's one of those things that frankly counsels moved very quickly and assumed all that data was there. So they just want us to go straight to e-discovery. We stopped, we paused, we verified the data, and then realized we didn't have it all, which led to a follow-on acquisition and follow-on bloating of data, but ultimately satisfied the request we were tasked with. Second example, we had an investigation into an insider threat group. The group was getting ready to leave a particular company, take a bunch of research they felt they owned, even though contractually the lawyers disagreed with that, and we were received data. The examples here in the screenshots allowed us to heat map the actual comms that would have been provided by the other side, the opposing side. And we realized very quickly, frankly, within about 40 minutes of receiving the data with the heat mapping, that we did not only not have it all, there were large gaps, which indicated redaction of data, which was actually in violation of the court order that we were trying to satisfy. So we were able to go back very quickly to counsel, be able to respond back that we did not only not have all the data that had been demanded by the court to be turned over, that we also had what appeared to be secondary redactions in the data that had been scrubbed before it had been passed to us. Thankfully, the judge was very upset, and we had a very good outcome on that one. Last example, this is a great way quickly to understand if the data you're getting from potential third party, like in that last example, is true and what you're expecting. Sometimes we rush, all of us do, right? We rush into the analysis aspect of this. We rush in to satisfy the request. This is a quick way to give you a quality control check to make sure you have it all. You're not missing blobs of data you would expect to be there, and then you can move forward.
Thank you, Devin. And just two more quick little callouts on this slide. If you are familiar with that data set, you spent the time to actually understand which elements, which fields are included, you can quickly start bringing together little one-liners like that PowerShell script there to start returning conversations or messages from just a specific user ID. Again, if you put in the time to understand your data set, you can start formulating a pathway to move through with the actual investigation. And that's where we come to the actual analysis here. Once we have that foundation of what we're looking at, and we think we understand the data set, we start to formulate a way to actually get the content we want, which was part of that outcome right in the beginning. And then we can talk about the channel types. There's 4 channel types in Slack, and we've categorized them into 2 real sets there. There is static membership from the multi-party instant messages and the direct messages. This just means that when you create a conversation, those are the communicators. It's very strict. That's very simple. As you move over to the dynamic membership channels, there are now the public and private channels. Users can basically be a part of these channels at their own discretion. They can join, they can leave, they can be kicked, whatever it takes. We just know that is not a fixed list. If you're trying to identify where a user was communicating, that adds a bit more of a challenge to how we're searching across that content. So our first instinct is to fall back to those informational files, because across those channel types, there are listings of the channels included, given in this export, as well as the membership. But we want to verify what we know about this data. We want to know if it's really a historical listing of the users that could communicated, perhaps have messages in those channels, or if it's a pin snapshot in time. And very quickly, we can come up with a test to validate this. You look for those membership channels or those dynamic membership channels where users have left those channels. There will be a message from the system that says so long, goodbye from that user. And then from there, we know they have left. Correlating that in time to our snapshot and the actual informational files, we can tell that no, it's not historical. So we cannot rely on those informational files for what we're trying to do, which is determine where users were and when. So with that known, we fall back to a brute force search of those user IDs across those conversations. We know the users, we know the channels they are likely going to be in now. And with understanding that the leaving messages from those users will give us a cutoff date for that content, we know the time range for those users for those channels. So very quickly, just by understanding our data set, making sure we're validating anything we think we know about it, we can arrive at a viable investigation pathway and be able to retrieve this content. And of course, now that we've preserved the actual attachments in this, we can package it up all nicely and make sure it's sent to the eDiscovery team for some part of that privilege or sensitive data review. And just touching briefly on the OODA loop, I know this is a model that's often touched on in the forensic community. It's actually from the Air Force, I believe. And all it is saying is that as an iterative loop, you're supposed to be observing, orienting, deciding, and acting. And from a forensic, very scientific perspective, this is what we're doing. We are observing the data as it comes in, making sure we understand all the elements that are coming to us. We are orienting ourselves with that data, starting to formulate hypotheses about how we can approach our investigation. We decide on a pathway, decide on a method of using this data to conduct our investigation and move towards that output, and we execute this. And as a loop, all it means is that as we encounter new information, we reiterate through this process.
So our last case study here is focusing on tertiary data. So we had an incident where a client was experiencing a ransomware event. There had about 1,000 hosts affected. The threat actor was claiming about 40 terabytes of data that was being exfiltrated. And a part of that process, we received a file listing from the threat actor. So it's not uncommon to see these kind of requests or have these requests incorporated within kind of an investigation. You can see the prevalence of that in a project called Ransom Chats on GitHub, where there's going to be requests for samples, requests for decryption, proof of decryption, and file listings. While this is not necessarily a trusted data source, it's certainly one that we can build confidence in by incorporating those primary source artifacts and very different key markers across the network. So this is not necessarily something that we should be confident in, as we discussed. It should be something that we should absolutely be cautious of, but we think that by adding additional references across the environment and being able to incorporate that sensor data as well as our file folder accesses, we can start to build confidence in that data. But ultimately, these are tertiary sources and we shouldn't be trusting them. The threat actor, after all, is trying to extort you and your client. But that's why we at Kroll have a team which has been really defining that process. Shout out to Brian McKenna and Matt Armbaum. So that really process really kind of starts with the initial capture of the file system. And that's where we're going to try to preserve the state as much as we can, because there's ephemeral files. Files are getting deleted, moved across a vast network. And once we've been able to do that, we can start and we receive the file listing. We really want to look to normalize that listing because of the variety of formats that you can receive. There's across operating systems, you can receive directory information or no information at all, file names or times. It's a variety of options that need to be really looked into, and that's kind of where we spend a bulk of our time looking into those file listings.
One of the jokes we have, and I imagine most of you that work ransomware, organized crime group-based investigations, we have an internal joke that we'd love to come up with a tool that's free, that all these threat actors would actually use to create file listings. So they stop using all the crazy commands they come up with. For those of you who have done these, I can only imagine how many times you've seen different file listings that you've had to try to normalize to then go reconcile with the data that is probably believed to be at risk within the organization. It is everything from absolute garbage tooling, garbage file listings, to very good command line structures we can actually go back one-to-one and find. But as you can imagine, like with the one screenshot we've got there, the pluses, the minuses, all of the funky ASCII code that gets dumped into these file listings, it makes it interesting, right? We've got over 80 different scripts that normalize these from probably over 100 tools we've seen threat actors use, and it is ultimately bundled into a tool we have. Again, reach out to us. We're happy to share kind of the knowledge in this. The methodology really is, how do you take the file system listings, and then normalize that against the file listing text files that you're getting back from a threat actor and figure out a commonality, because they'll almost never have a one-to-one. So then trying to figure out why do you have the differences in the data and reconciling that so you can move it forward.
Yeah, definitely. And that's where we're kind of comparing our threat actor listing to maybe our primary sources, where we've maybe been able to identify, for example, firewall logs, where exfiltration is coming from. But if that doesn't really provide us with enough matches or a high confidence listing, that's where we're going to seek to try to correlate the data to maybe other machines or hosts that we've been able to find. And once we kind of have direction from counsel and been able to provide that high listing, we can begin collecting that data so we can get it to review. So with these challenges, as Devin said, that we're going to have a variety of listings. So we've observed about 30 plus different formats of listings. And what the team is trying to look for is different data points. File name is obviously one, but as where we can achieve, we're going to look for absolute file paths. But the problem is that we start coming into regional settings, and we start coming into operating system settings where certain characters are allowed based on those settings. And they really start causing problems to your scripts, especially when you have different ways that you can represent a hyphen in email and you have emojis. And when we start talking about comparing and correlating, terabytes of data across thousands of hosts, you start running into big data and big problems. So we really seek to try to find efficiencies where we can and parsing the data across the network. Brian McKenna was kind enough to provide a secondary script there for parsing file trees. So as we said before, file name alone is a weak identifier. So we look to try to match different levels, multiple levels of the parent folders. Being able to do that will allow us to potentially identify any host that we may not have visibility on or enough artifacts to support. This especially becomes important when you have large networks where files can have many of the same names, or corporations are using project folder templates where almost all of the files within a folder are the same. As you can match higher up, you can build your confidence that that file listing or that file was exfiltrated from a very specific host. It's an iterative process where we're referencing those primary data sources to raise some confidence, but then we're also expanding that focus, pulling MFTs across a whole network if we need to. So with unconventional data comes unconventional problems. You can get, you can try, using all the command switches you want and try to generate listings and just try to accommodate for everything. But you never know. Someone may send you a listing in HTML or screenshots of a file listing. But being able to document that process and having those experiences recorded allows you to build off of that once you solve those individual and unique problems per threat actor or listing. So hopefully we've been able to show at least how you can turn tertiary data into something that's a little bit trustworthy, and you can build confidence in that process and being able to integrate it into your investigation to either refute the threat actor claims or confirm your forensic investigation.
Awesome. Thank you, Anthony. I like your point that threat actor data is still data. However, if we start comparing that to our primary sources, we can actually use it as a foundational part of our investigation. But it's not trust, it is verifying, as Devin said. And just a quick little head nod to some recent changes in the industry which fall under those secondary sources. This was Microsoft's change to actually grant some of those critical security logs by default to their licenses. So they're not gating this just by the amount of money you're paying them. They're making it available and making it available at no additional cost.
Look, I think our time's up, but ultimately that's hopefully exciting for those of you that are doing BEC type investigations. Hopefully within the next month or two, we'll start seeing some additional auditable events and evidence that allow us with specificity to start identifying what threat actors are actually accessing when they're going through a BEC lifecycle.
Thank you. And this is the last slide. And the takeaway from all this is that investigating these data sources is not magic. It's still a science. There are ways to make this defensible. There are ways to make this absolutely bulletproof and repeatable. We're identifying what we have. We're informing ourselves about that content. We're investigating, and we're constantly iterating to make it a better process. That's it. Thank you.
Thank you all.